Bismillah, alhamdulillah, salatu wassalamu ala rasulillah. The class of today is about section 3.4. As you can see from the title of this section, it is not about something new. It is about the real zeros of polynomials. So you can consider this section as a 3.2, 3.3, just in a more advanced way. If you remember, in 3.2, we learned how to sketch the graph of polynomials. What you need to know if you want to sketch the graph of a polynomial? The zeros. And to know the zeros, what you need to do? Factor. Now, there are many polynomials that we cannot factor by the methods of chapter B. And I told you that in chapter B, that we will learn other techniques in chapter 3. This is the section that you will learn, in which you will learn how to factor by new techniques. So this in this section, you will learn mainly two skills. The first skill is how to find all the possible rational zeros of a polynomial by using the rational zeros theorem. The second skill that you will learn is how to use the Descartes rule of signs, how to know how many positive real numbers, real zeros, and how many negative real zeros. Let's say to be more accurate, possible, the number of possible positive or negative real zeros. Or look at this, consider this polynomial. Can you factor it by the methods of chapter B? Let's say immediately, can you factor it immediately? Even if you think about kind of groupings, to not be that easy or that direct. But indeed, this polynomial can be written like this, in this factored form. So this is the expanded, the first line is the expanded form, the second one is the factored form. The question is how they factor it like that. What they did. This is what we are going to learn today, inshallah. What I just want you to notice, what are the zeros of this polynomial? 2, 3, -4. Can you look at them again? There is something in common between them. These three zeros are factors of 24. They are related to 24. Why is that? In fact, this is coming from the rational zeros theorem. The rational zeros theorem says, in general, if a polynomial of degree n has integer coefficients. So first of all, we are talking about polynomials with integer coefficients. If they are not, we cannot apply this theorem. And the leading coefficient is not 0, and the constant term also is not 0. By the way, if it is 0, if the constant term is 0, it is not a problem, because you will take x as a common factor and you will have another constant term. So you can continue working. So these are the conditions. In every theorem, there are conditions and conclusion. So if these conditions are satisfied, what they are, we have coefficients, integer coefficients, and the constant term and the leading term are not 0. Then, this is the conclusion now. Then every rational zero of this polynomial is of this form, P over Q. What is P? What is Q? P and Q are integers such that P is a factor of the constant coefficient. So P is coming from here, from the constant term, and Q is a factor of the constant of the leading coefficient. So it is just here about what? 24, the coefficients of 24 and the coefficient of 1. This is the easier case, by the way, when you have the leading coefficient is 1. If you have the leading coefficient is 1, just you need to focus on the factors of what? The constant term, like the previous example, the one that we have here. Let's take an example. I think it will be much easier if we take an easy example. Who can tell me what he wants you here to find all the rational zeros? Before talking about all the rational zeros, we need to find all the possible. You have to distinguish between all the rational, exactly what they are, and the possible rational zeros. So they are nominated to be zeros. So to find the possible rational zeros, you need to use what? What is your tool? The tool that you will use is the rational zeros theorem. The rational zeros theorem says what? The possible rational zeros of any polynomial will be the factors of the constant coefficient over the factors of the leading coefficient. Here it is. Now, what in our case, the leading coefficient is what? So this one here, it is positive or negative 1, the coefficients of 1, the factors of 1. And here we will have what? What are the factors of 2? Positive or negative 1, positive or negative 2, because negative 1 and times negative 2 will be 2. So we will take the positive and the negative factors. So how many possible rational zeros, ya shabab? We have 4 possible rational zeros. But as we will see in chapter, I think in section 3.5, yes, in the next class, inshallah, we will see that we have here a polynomial of degree what? 3. So according to the fundamental theorem of algebra, this polynomial of degree 3, it has at most 3 zeros. Some of them, they might be rational, some of them might be irrational, some of them might be real, non-real, all kinds of zeros. So we have now 4, but not all of them will be, of course, zeros. Okay, how to know now? These are nominated to be zeros. How to know which one of them is a 0, which one of them is not? You can substitute, yes. So you will start with what if you want to substitute? It is natural to start with 1 and with positive 1, not negative 1. So if you put x equals to 1, what you will get? 0 or not? Yes, it is. It is 0. Now, what you will try next? Negative 1. Let's try negative 1. Is it a 0? No. It is not. Then you will try 2. It is not. Then negative 2. It is a 0. So we are done. These are all the rational zeros that are nominated to be. There are 2. What is the third one? One of them is repeated. Which one of them is repeated? How to know?
Because we multiply, but we have multiplicity 2 in the negative 2 equation, it will be 4. When you substitute, so we have x plus 2 squared multiplied by x minus 1.
I cannot see your point, Mansour. By the way, here we have 2 zeros, 2 rational zeros, 1 and the negative 2. One of them, as you said, one of them is of multiplicity 2. One of them is repeated. So this is why I advise you, if you want to check if they are zeros or not, I advise you to do what? To do synthetic division. We have here 1, 0, negative 3, 2, right? These are the coefficients of the polynomial. Divide by what? By 1. What you will get? 1, 1, 1. We will try 1. We will check that if 1 is a 0 or not. We like substitution. This is better than substitution. Why it is better? Let's see. Now we will have what here? 1, here negative 2, multiplied by 1, it is negative 2. You will get what? So it is a 0. Now we have the first factor. So this is equals to x minus 1. This is the first factor. 1 is a 0, then x minus 1 is a factor. Previously, when we only substitute, we were able to know that 1 is a 0, but we don't know what is the other factor. But here we know what is the another factor. What is the another factor? X squared, 1x squared plus 1x minus 2. So here we are. So this is the gift. This is the offer. If you use the synthetic division, you will get the remaining factors. And this one, it is a polynomial of degree 2. You can what? You can factor it. What is it? It is x. So we have what? We were having x minus 1. Now we will have what? X squared plus x minus 2. It is just x minus 1 times x plus 2, right? Which can be written as x minus 1 all squared times x plus. Now we know which one of them exactly and surely which one of them is what is repeated. There is another way to know if it is repeated or not. Divide by 1 again. Look what will happen if we divide by 1 again. What do you expect? We will get the remainder 0 also. So this will show us that it is a 0 of multiplicity 2. So you will get here 1, bring it down, you will have 1. It will be 2, add, it will be 0. And this is the last factor. What is it? X plus 2. And we get all the 3 factors. Yes?
If we do the synthetic for the 1 and we get 0, so no need for do it for another number.
Why not? You have 3. This is what you will see later, Shabab. How many possible rational zeros you have here? The maximum number of zeros is 3. So you still have. We have 4 nominated here. So it could be any one of them. Yes.
What if we can factor?
If you can factor, no need to do that. If it is easy for you to factor, factor.
No, I mean after we substitute with 1.
This is what we did. If you cannot factor, you mean?
Yeah.
If you can factor or if you cannot factor, it depends on the polynomial that you have. We will have another example that we cannot factor. We will use the quadratic formula if it is quadratic. If it is not quadratic, you will apply it again. If there is no rational, they might be irrational. They might be not real. We will see that, ya Shabab, with other examples in the next slides. So now we have here like an algorithm for finding the rational zeros. So these are guidelines for you. To find the rational zeros of any polynomial, what you need to do, you need to list all possible zeros. How to do that? By using the rational zeros theorem, which says that the factors of the constant coefficient over the factors of the leading coefficients. Then divide, use the synthetic division, better than using the substitution. Maybe you will, when it is about 1 and -1, you can substitute. But even if you get it 0, you need to go to the synthetic division. So you will work twice. One is better. Go to the synthetic division. Then divide, of course, to find the 0. Then repeat this process. Repeat step number 1 and step number 2. Find the possible rational zeros for the new polynomial that you will have. It will be 1 degree less. And also divide, use the synthetic division. Now you have here, Shabab, here the method 1, 2, 3, and you have here an example. Please write this polynomial in factored form and find all its zeros. What you will do? What you need to start with? Yes. You need to list all the possible rational zeros. So what you will do? According to the rational zeros theorem, you will write down all the factors of 6 divided by all the factors of 2. So this is the possible rational zeros of P will be factor of constant term over factor of leading coefficient. They will be factors of 6 over factors of 2. What are the factors of 6? 1, 2, start from 1. 1, 2, 3. After the half, 3 is the half of 6. Jump to 6. And the negative of them, positive or negative. So they will be positive for -1, positive for -2, positive for -3, positive for -6, divided by positive for -1, positive for -2. Then what you will do after that? You will do positive for -1 divided by positive for -1. So how many? 2. Then positive for -1 divided by what? By positive for -2. How many you will have also? 2. So this is what you have. Positive for -1, positive for -half. These are the first 2 you will do if you divide. You can do what I think I did here. I divide all of these by what? By positive for -1. So these are the first 4 that you have. Then divide all of these by 2. You will get, without repetition, of course, you will get this. For example, here, when we divide positive or negative 2 by positive or negative 2, you will get positive or negative 1, which is already we obtain. It is repeated. So how many nominated rational zeros? How many possible rational zeros? We have here what? 12. 12 nominated numbers to be rational zeros for this polynomial. Continue. I will leave the rest for you to continue. Yes, let's go to the algorithm, the guidelines. Yes, good. During that, Shabab, I will pause the recording and distribute the grades of the last semi-quiz. You need to factor. So you to factor, you need to find first the possible rational zeros. So how many possible rational zeros? We show that we have 12 possible rational zeros. Now, what you will do to start? You start with what? With one. Which one of them? It is not practical to start with 3/2, for example. You will start with 1, -1, 2, -2, 3, -3. Some of you, they prefer to start with the positive ones to avoid any errors when you work with the negative signs. So it is natural to start with 1. Let's start with 1. Unfortunately, it is not a 0. Okay? But no problem. Don't worry. Even if you substitute or if you divide, it will be almost the same time. What you will do next? Which one you will try? 2. Let's try 2. It works. 2 is what? 2 is a 0 because the remainder is what?
0.
The remainder is 0, so 2 is a 0. So we have one factor now. What is the first factor that we have? X minus 2. And for free, we had another factor. Here it is. What is it? The original one, it was of degree 3. This will be of degree 2. Now, this is, of course, trinomial, polynomial of degree 2. We can factor it with the techniques of chapter P. How to do that? It will be 2x multiplied by x. This is 3 and 1. Let's try like that. We need the bigger product to be positive. So this is positive. This is negative. And here we are. These are the 3 factors. We were able to factor it. Good. I think we are done with this. We have 3, and we are lucky here. All of them are what? Rational. All of them are from these nominated. Let's take one exercise. This is a recitation exercise. List all possible rational zeros given by the rational zeros theorem for this polynomial. How to do that? How they will ask you about this, by the way, in the exams. In the written, I may ask you list all of them. No, I think also the sum is too much, especially if they are. I think they will ask about the number. The number. So let me ask you here, how many possible rational zeros for this polynomial? And give me your answer. For the sum, by the way, always will be 0. Do you know that? Because you will take positive or negative. They will not ask you about the sum. What you will do? Can you give us a hint? Million? What is that? No. So you will just write here the coefficients of what? The factors of what? The factors of 8 over the factors of 12. So what are the factors of 8? Positive or negative 1, positive or negative 2, positive or negative 3 is not 4. 4 is the half of 8. That's it. Why they are million? Now they will be divided by the factors of what? The leading coefficient, which is 12. What they are?
1, 2, 3, 4, 6, 12.
Then what? You will divide all of these by what? By negative 1. By positive or negative 1. You will get them as they are. Okay? So how many so far we have now? 8. Then you will divide them by what? By 2 without repetition. So let me just do the first steps for you. Positive or negative 8. Now what will be the next one? You will divide them now by what? by positive or negative 2. So they will be what? This will be positive or negative a half, positive or negative 2 over 2, which is 1. It is already there. Okay. Positive or negative 4 over 2, it is 2. It is already there. Positive or negative 8 over 2, it is 4. It's already there. Okay. Now, can you proceed in the same way? You can continue the same way. Now you will do what? You will divide them by what? By 3. You will get positive or negative third, positive or negative 2 over 3, positive or negative 4 over 3, positive or negative 8 over 3. Right? Now you will divide them next by what? By 4. At the end, you will end up with this list of possible rational zeros. How many? 24. Yes, 24 possible rational zero for this polynomial. Of course, they are asking about the possible, not about the rational. If they ask you about the rational, you need to find them exactly what they are. Okay. Now let's try to solve this example. Let P of X be this polynomial of degree 4. List or find all the zeros. We need to find them exactly what they are. All the zeros, rational or not rational, all the zeros. Then sketch the graph. And you know what you need to sketch the graph. You need the zeros, and to find the zeros, you need to factor. Okay. So let's start with part A. How to find all the zeros of this polynomial? You need to start with the possible rational zeros. So you need to apply the rational zeros theorem. So we are lucky because the leading coefficient is 1. So just we will look at the constant coefficient. What is the constant coefficient? 10. What are the factors of 10? We have positive or negative 1, positive or negative 2, positive or negative 5, positive or negative 10. So we have 8 nominated numbers to be rational zeros. Which one you will start with? It is natural to start with 1. Are you going to substitute or you will divide? Divide. Let's do that. Oh, we have all of them here. So if you tried 1, look what happens. It is not. You will go to 2. It is not. To 5. طبعا he avoid to use the negative ones. You can go to negative 1, by the way, after 1. No problem. Now we are lucky because we have what? We have 5 as what? As a 0. So we have now one factor. What is the first factor that we have? X minus 5. And also we have the other factor here. So we can now write this polynomial as x minus 5 times x to the power 3 minus or plus 0x squared. There is no x squared here. Minus 5x minus 2. Can you factor this? If you can factor it, do that. If you cannot, what you can do? Repeat what you did before. So now again, the leading coefficient is what? 1. And the constant term is 2, negative 2. The factors are what? Positive or negative 1, positive or negative 2. But we will use only negative 1 and negative 2. Why?
Because 1 and 2 is
we use them already. لو كان فيهم خير كانوا ضبطوا من البداية. They are not, because they are not zeros. 1 and 2, if they are zeros for the original, they will be factors. So they are not. So don't try 1 and 2 again. Try negative 1 and negative 2. Yes.
Is it possible to have all the solution negative?
Why not? Yes. Why not?
So I shouldn't try all the positive numbers.
We will see about negative and positive when we study the Descartes rule. We have a rule that can help us about how many positive, how many negative. So we will try negative 1 and negative 2. It is natural to think about what at the beginning? Negative 1. I advise you for 1 and negative 1, just look at the original one and look if it is 0 or not. If you tried negative 1, it will not be a 0. Negative 2 will be a 0. Here it is. So you will divide the last line that you have here. You will divide it by negative 2, and it is a 0. Okay. Now we have another factor. What is it? X plus 2. So now we have the first factor that we had is x minus 5. The second factor is x plus 5. The last factor is this, x squared minus 2x minus 1. Can you factor this?
Yes.
What is it?
X minus 1.
X minus Minus 2? Uh-huh.
X plus
Are you sure? No, be careful. You cannot factor this bit. By the way, try. It is prime polynomial. You cannot factor it, of course, but you can find its zeros by the quadratic formula. Here they are. They are not rational. They might be irrational or not real. So they are irrational. So we have, for this polynomial, we have 4 zeros, 2 rational and 2 irrational, 2 positive, 2 negative, right? Now the second part is about sketch the graph. How to sketch the graph of this polynomial? 3.2 and 3.4 now together. How to sketch the graph of this polynomial? The end behavior, it is a polynomial of even degree with positive leading coefficient. So it will be up to the left, up to the right. And we have 4 zeros, all of them of multiplicity 1. So it will be cross. We will have cross at each one of them. It looks like this. If you try to sketch the graph, it will be like this.
We can sketch the complex number.
Where are the complex numbers? They are irrational. It is 1 plus 1. This one, for example, it is like 1, 2 point something. This is like 1 minus, it will be 0 point something, negative. So here it is. If you have, they are not x-intercepts. We will focus more on that next class in 3.5. The x-intercepts are real zeros. They are not complex. Good. It will be above the x-axis or below the x-axis. Like x squared plus 1. It has 2 zeros, I and negative I, and it is always above the x-axis. We will see that in section 3.5. Now, we have here a rule that can help us to reduce the time and the process of finding the rational zeros. It is called the Descartes rule of science. Descartes is the same mathematician that he invented, of course, the XY plane, the coordinate plane. And, you know, it is a French name, so this is why it is pronounced in a different way that it is written. Most of the letters are silent. Descartes rule of science, it is about what is the possible number of positive real zeros and negative real zeros, not only the rational, all the real. But before studying this rule, you need to know one terminology, the variation in sign. What we mean by variation in sign. If you have a polynomial with real coefficients written in a descending order from the highest power to the smallest power, then the variation in sign occurs whenever the adjacent coefficients have opposite signs, when they change their signs from positive to negative or from negative to positive. Like this polynomial, look at this polynomial. It has 3 variations in sign. Why? Because you started, of course, they are ordered from the highest to the smallest power in a descending order. Positive, then what? So this is one variation. Then negative, negative, there is no variation here. Then negative, positive, this is the second variation. Positive, positive, no variation here. Then positive, negative, it is that we have here 3 variations. So this, the number of variation here is 3. These are more examples. Look at this. There is no variation here in sign. So the number of variation is what? 0. In the second one, 1. In the third one, 2. The Descartes rule of science says, if you have a polynomial with real coefficients, then the number of positive real zeros, the number of positive real zeros of P of X is either equal to the number of variation in sign of P of X or less than that by even whole number. Is it clear or I should repeat it? This says that if you have a polynomial and you want to know how many positive real zeros, the number of the positive real zeros will be the same as the number of variations of signs, or less than that by even whole number. Example, if you have 3 variations, like the one above here. So if you have 3 number of variations in the polynomial, then the number of the positive real zeros will be 3 or 1. It will be 3 or 3 minus 2. And you will stop. This is what they meant by even whole number. You know, the whole number starts from 0. Now, for the negative, the number of the negative real zeros will be equal to the number of the variations in the signs of P of negative x. When you replace x by negative x, the number of variation in that case will be equals to the number of the negative real zeros will be equals to the number of the variations or less than that by even whole number. I think it is better to have an example about that. But before that, yes.
Variation number is the negative sign, variation sign.
How many times the sign has been changed from positive to negative or from negative to positive? Let me give you this interesting case. X squared minus 2x plus 1. How many number of variations here? We have 2. But this one, in fact, it is just x minus 1 all squared. How many zeros? So it has positive zeros, 2 or what? The number of variations. Let me do it here with another color to be more clear for you. We have here positive, negative. This is one variation. This is another variation. So we have 2. How many positive zeros? 2 or what? 2 or none. 2 or 0. But indeed, this polynomial, it is just x minus 1 all squared. It has 1. So what is that? This is repeated. So in Descartes rule of signs, a 0 with multiplicity m is counted m times. And this is the example that I told you about. It is a 0 of multiplicity 2. Now, use Descartes rule of signs to determine the possible number of positive and negative real zeros for this polynomial. Who can tell me how many positive real zeros for this? Positive and negative. You will start with P of x. How many, what is the number of variations here? No, 1 only. We have 1 number of variations. So this means that how many positive? Only 1. If you did 1 minus 2, you will go to a negative number. It is not a whole number. So we will stop at it is 1 only. So this polynomial, it may have 1 positive real zero. Okay. Now, what about the negative? 3 or 1. How to know that? You need to go and replace x by negative x. So the positive, the one with even power, it will stay the same. Without power, it will be changed. So we have now 3 number of variations. This means that we have what? How many negative real zeros? 3 or, let's count the all cases. And this is what we have. Now let's consider all the cases. So now we have positive, and let's say this is negative, just for short. So we may have positive, how many?
1.
Only 1. 2, for the negative, we may have 3 or 1. So in this case, how many real? If we have 1 positive and 3 negative, how many real we will have? 4. And if we have 1 positive and 1 negative, how many real we will have? What about the other? It is of degree 6, and as we will see in the next section, if you have a polynomial of degree n, it has at most n zeros. So indeed, the others are what? Here we have 4, they will be 2, and if it has 2 real, it will have, of course, 4 non-real. Let's take an example. This is a recitation exercise, an easy one. Before going to the last example, according to the Decart rule of signs, which one of the following is false about the zeros of this polynomial? Which one is false? Just here, you need to apply the Decart rule of signs. Just you need to see how many positive and how many negative real zeros. For the positive, how many? It is clear from here. For the positive ones, what is the number of variations? 1, 2, 3. So we may have what? So the positive, for the positive, we may have 3 or 1. For the negative,
Why 1? 1 for 1?
3 or 1. We said the number of, this is the rule of Descartes. It says that the number of the positive real zeros equals to the number of variations or less than that by even number. Now for the, you will replace x by negative x, what you will get? Negative x to the power 5 minus x to the power 4 plus 2x to the power 2 plus x minus 1. How many variations? We have what? We have 2. And this is another one. So the number of negative zeros will be what? 2 or what? 2 or none. 2 or 0. So it is clear now which one of is not true, is false. Which one of the following is false? Just from knowing the number of negative zeros will be 2 or 0. Look at the first one. What does it say? Is it possible to have 3 negative zeros? No. So the answer is A. The one that is false is A. Let's continue. Let's continue understanding the process. Now, when we have 3 positive and 2 negative, how many real we will have? 5. And how many non-real? None. If you have 3 positive and 0 negative, then you will have what? 3 real and 2 complex. Now, if you have 1 positive, you may have also 2 or 0. 1 positive, 2 negative, you will get 3 real and 2 what? Non-real. 1 positive, 0 negative, you will have 1 real and 4 what? 4 non-real. You can now answer any question. We were lucky here because this is the first one, but it might be the last one. So you need to go over all of them. This is possible. 3 positive possible. 1 positive is possible. 1 positive is possible. But 3 negative, not possible. False. Now let's go to the last, I think, example. We don't have time to do more. Factor this completely. Imagine that I give you this in exam 1. What you will do? You will drop the course. Now you are able to factor. You have a polynomial of degree 5. You cannot factor it with the ideas of chapter P. What you need to do? Find the possible rational zeros. Yes, the process might be a little bit long, but at least you know how to do that. So you will start with the possible rational zeros by dividing the factors of 9 by the factors of 2. These are, we have 12 possible rational zeros. Which one it is better to start with? Of course, 1, then negative 1, then 3, then negative 3. This is natural to think like that. But let's get benefit from the Descartes rule of science. This will help me to know how many positive, how many negative. Let's just take the positive. How many positive? What is the number of variations? 1, 2. So we will have 2 or what? 2 or 0. So if I can get 1, I will know that there is another one. If there is no one, I will know that there are 2. So I will not try more than 2 positive numbers. This is what is good about this. Will reduce the amount. So let's focus on applying the Descartes rule. Again, you can use 1, then negative 1, then 3, then negative 3, then go to the fractions. But let's start with let's do it this way. Of course, he started with a half. No need to start with a half. Let's start with 1. So if you start with 1 and you get the remainder, what? 0. So what does this tell you? This case is not possible now. Khalas. Because we have 1, we should have another one. The another one is not a half. Because look here, it is not. Is it possible to be 1 again? Why not? Why not? It could be of multiplicity 2. So what you should do, you should try 1 again. So you will now repeat 1 again here. Divide by 1. I think we have it. The first factor that we have x minus 1. This is the next one. We are lucky here because we still have the same leading coefficient and the same constant there. So we still have the same nominated numbers. So we will try 1 again. Look, he tried again, but unfortunately it doesn't work. So it is not a 0 of multiplicity 2. It is only 0 of multiplicity 1. Okay. So we still looking for 1 positive, right? So what we will try? This is normal to think about 3. So we will try 3. Try to do that. it will not be. If you try 3, it will not be. So 3 over 2, it works. 3 over 2 will be a 0. And we will not try now any more positive. We will not try positive 3 and positive 9, for example. So we left up with negative choices now. So it is natural to think about what? Negative 1, negative a half, and negative 3 as well. So we have now, look how many factors we have so far. We have x minus 1, x minus 3 over 2, and this is the remaining, of course. And you can see here that we have 2 as a common factor. Factor it out and cancel it with 2. This will be 2x minus 3 over 2. Cancel these 2 with that 2, and you have this at the end. Now this is the polynomial that we left up with. How to factor this? You will look at the coefficients of the constant term, because the leading term here is 1. So it will be, what are the denominator? Positive or negative 1, positive or negative 3, right? No. The denominator are negative 1 and negative 3 only. There is no more positive. We had only 2, we use them. So you will try, of course, negative 1, and it works, I think. Negative 1 is a 0. So now we have what? We have x minus 1 times 2x minus 3 times x plus 1 times x squared plus 4 plus 3. And you know how to factor this one. It is quadratic. And here it is. Look, if you tried negative 2, negative 1 from the beginning, it will be of multiplicity 2. You can use it twice, and the process will be much easier. We have now 4 zeros. One of them is of multiplicity 2. How to sketch the graph? This is a polynomial of degree what? You remember it was of degree what? It was of degree 5 with positive leading coefficient. So it will be down to the left, up to the right. And it has tangent at negative, and at the others it has crossing behavior like this. Look, just focus on this one at negative 1. What happens? There is no crossing, it is just tangent. That's it. This is section 3.4. We will practice more tomorrow by solving the recitation exercises, inshallah. Thank you, and see you.